Hi, and welcome to Engineering 255 Statics. In this episode, we're going to talk about Chapter 8. The topic of the Chapter 8 is about friction. Friction is a force. As we know, a force should have a direction and also the amplitude. So we're going to have two videos talk about friction. The first video is going to focus on the explanation of the friction, how you determine the direction and amplitude. Then we will go to the next episode where we'll look at a little bit more complicated situation so you know how to deal with the situation that has involved with the friction. All right, so first, I wanted to show you some of the pictures and give you understanding what we will cover in this video. The first picture I want to show you on the right upper corner is the car in the snow. Now we know if you're driving a car in the snow is very dangerous, especially if you don't have a snow chain. The purpose of the snow chain is actually to increase the friction, because without the friction, then you have no control of the car. The car can move any direction that it wish. And that is the situation when you drive the car on a snow road. A regular road gives you a friction between the road and the tire. And if you don't have a friction, the car will skid, and that is dangerous. So, and if you think about how you walk, actually the walking depends on the friction as well. So the lower left corner shows you how this friction can help us to walk. If there's no friction, then we will skid on the road as well, just like a car. So any kind of a vehicle, it really depends on the friction. However, we also know that friction will cause the loss of the energy as well. So when you are running a machine, you don't want friction in certain situation because any of the friction is going to waste some of the energy. But some of the things that we still depends on the friction. And think about if you want to design a brake system. A brake system is try to stop something, move, and that is depends on heavily on the friction. And as we said at the very beginning, it is very important for us to know if you want to design a brake system, how much of the friction do we need and what is the direction of the friction. So that is going to be the topic of this chapter. We're going to start with some important observation about the friction first. So the friction is defined as the force of the resistance. So it's resisting the motion. And we don't want the body to slip, and we want to stop that kind of a motion. So if you have a block, you pull the block horizontally, and you try to make it move horizontally. Without the friction, it certainly will move. However, if there is a friction, it would not move. So the friction is the force trying to prevent it from moving. Therefore, the force of the friction should be against this pulling force, which is the P. So the friction force is going to be opposed to the direction of the motion. And that is the direction, but the direction is actually it's actually not perpendicular, it's parallel to your opposing force direction. So if you pull horizontally to the right, the friction will be horizontally as well to the left. In the experimental, we find out this friction force depends on several factors. One of the important factor is how much of the normal force that is. The normal force is normally depends on the weight of the object. So even though the friction force is not in the same direction as the normal force, but it still depends on the normal force as well. If you look at the bottom part here, which is a free body diagram of the situation that you're pulling a block on a flat surfaces, we take out the bottom part, which is the contact surfaces. When we take out anything from the body, we need to put the reaction force, where the reaction force is the friction force, and there's a normal force. So the normal force is the supporting force to the block. The block itself has a weight going down, and the friction force between the surface and the object is going to the left in this case. But if you look at the surfaces, the bottom surfaces, that friction force will be the force goes to the right, which is opposite to this, because friction force in this case is also an internal force between the block and the contact surfaces. You can use the equilibrium equation. The equilibrium equation will be the summation F equal to 0 and also the summation moment equal to 0. So these two are the summation force. And one is the x direction and one is the y direction. This one here is our summation moment. So how do we look at the moment? Let's look at the moment with respect to the point of O, which is this point right here. You have a P here with a lever arm of H. It will try to make it go this direction of the turning. You also have another force, which is the weight itself here, that will make it turn to counterclockwise. And the lever arm is going to be A over 2. So that is how you calculate the summation moment. Now, if you consider about the normal force, and the normal force will also create some kind of rotation as well, and then you have to put that into consideration as well. So by doing the experiment, we try to understand, well, how much friction force that is such that the object would not move. A very easy example, a very easy experiment that you can do is actually just put a block on a table, and you slowly increase this P, and to see if the block does not move and how much P that I apply, because this P in horizontally, there's only two forces. It's going to be a friction force and also the pulling force. So pulling it to the right, slowly increase. If the block does not move, then friction force should be equal to the pulling force. For example, if you pull this one with 1 pound and this one is not moving, the friction force must be equal to 1 pound. You increase the pulling force such that this one is 5 pounds, and this will be 5 pounds as well if this one does not move. And this is what exactly this picture is trying to show. So you keep on increasing the pulling force, and we find out when you increase this one to a certain amount, you can start to see this block start to move. And that highest point is what we call the maximum static friction force. When the object starts to move, you are still experiencing the friction force, but the friction force is going to decrease. And this decreased amount, this friction force at this point when it's moving, is what we call the kinetic friction force. And you probably learned this one in the physics already, but I just want to emphasize that these two are different. This one is called the maximum static friction force. This one is the kinetic friction force. Okay, kinetic. This is the maximum statics. Over this whole range here are all called the static friction force, but this is the highest point that will prevent it from moving. Okay, so that is experimentally we can use this one to determine what is the maximum static friction force and what is the kinetic friction force. I want to point out two important observations here. In the no motion here, which is static, this friction force is proportional to this pulling force. So this is like a slope, right? There's a slope like this. In the kinetic friction force, this one remained the constant. Okay, it remained constant. And this will give us the equation that we use to do the calculation. So, which is this one here. So the maximum friction force, which is this one here, and that is this one here, is the impeding motion force that the highest force will stop it from moving. And we can calculate this one by using this equation right here. So the Fs represent the static friction force. The mu sub s is a coefficient. This coefficient is called the coefficient of static friction, and this number is normally less or equal to 1. So this number is a small number. It's going to be less or equal to 1. Normally it should be less than 1, and that depends on how the two surfaces interaction is. And this microscopically is like the roughness of these two surfaces. If that start to move, then your friction will become kinetic friction force, and this will be the force itself is going to be mu k times n, where the mu k is the kinetic friction coefficient. That is not the same as the mu s. The mu s normally will be greater than the mu k. So this coefficient is going to be larger than your kinetic friction coefficient. And that is the two most important thing that you need to know. Again, one thing I want to point out is this one is the maximum. Your static friction force could be actually less or equal to this one. So I will prefer to put a maximum at here. If you wanted to just look at the f of s, that should be less or equal to mu s times n, where the n is the normal force. So what is the n depends on? N depends on the weight. And here just try to emphasize to you as I point out, the Fs is the maximum. So your friction force is going to be less or equal to this F of S. So I will really like to put a maximum. So your F of S should be always less or equal to the maximum of the friction force. How do we determine this one experimentally? As we said, and you can actually do this by slowly pulling that to the right, and you can have a force gauge to measure how much of this P is. So as the device would tell you how much force you actually applied. But the other way you can do is that you can actually put the object in a plank and you tilt it. So if you pull a block like this and you slowly increase the angle until to a certain angle, it will start to slide. Just before it slides and you look at the angle is what we call the critical angle. And the critical angle tells you give you an idea how much of the friction force is. And we can do the calculation. This tangent of this angle, which is this angle here, is going to be your static friction coefficient. This is how we actually do experimentally to determine amount of the friction coefficient by using this very simple setup. We can analyze it to understand how this is coming from. And if we just simply take the block out, so this is the block, and we do the free body diagram. This is going to be a weight in this direction. And we will have a normal force in this direction. We will also have a friction force, and what is the direction of friction force? If this one move, this one will move downwards, right? So the friction force will go against the direction of the motion, which will be this direction. And we try to find out when is the friction to be the maximum, such that we can find out, because this one is going to be equal to mu s times m. So we try to find out what is the situation, and this amount of the force is equal to, and it should be equal to mu s times m. Then you look at this. So we have these three different forces. We need to use the equilibrium equation to find out what is the mu s is equal to. The mu s should be equal to this. If I decompose this one, right? If we decompose this one, and I should be find out how much of this force is equal to. So that's just like an x direction force, right? So that just says assume this one is the x direction force. And how much of the fx is equal to? Well, if we do, and it depends on the angle, right? So if this one is the angle, we try to find out what is this angle is equal to. Or let's make another drawing here to show you more better pictures. This is the n. This is the f of x, and this is our weight. Okay, and this is the critical angle. So if this is 90 degree and this is also 90 degree, then this angle will be the same as our critical angle. If you take a tangent of this critical angle, and that's going to be the ratio of this f of x divided by the n. And we want to find out what this fx is equal to f of s of maximum, and that is the situation that is not, this is the maximum friction force situation. And that's why you see this tangent phi of s is actually equal to f of s. This should be maximum divided by the normal force. And what is the f of s maximum equal to? The mu s times n. So you divide by n, that is our coefficient. And that's what this slide is trying to tell you. Okay, so if we have this block that is moving in the situation which is described, and you can take the summation of fx and summation f over y, and you make it all equal to 0, and that is you find out the mu s is equal to the tangent theta of s. Okay, this is kind of a repeat what we just said before. And so the critical angle will give you an idea what the coefficient is. And again, that angle, that coefficient should be less than 1. Before we show you some of the example, I just want to tell you the step of solving the friction problem. The first step is that you need to draw a free body diagram. The free body diagram help you to identify what are the forces, especially what are the force that is normal force, and if the setup has an angle, then you need to know what the angle is in order to find out how much of the component will be the normal force component. A second thing is that you need to also identify what is the possible way if the things will move, because it is going to help you to identify the friction force direction, which should be opposed to the direction of the motion. And a very important, you don't assume that your friction force is always equal to this, because this is the maximum. The friction force could be smaller than the maximum. Depends on the situation, right? Then you use the equation of the equilibrium, which is summation F, and summation moment equal to 0. That will help you to solve the problem. Now let's look at one of the very common situations that we can use the friction to solve a problem, which is similar to the one that we just talked about. Let's say a person is trying to push a closet and moving to the right direction. So you're pushing it with a force of P, and the closet itself has a weight, which is W, going downwards. And because you try to move it to the right, if it's not moving, you will have a friction. Even if it's moving, you still have a friction. That will be kinetic friction. Let's say this is an F, which is the friction force. The ground is going to give you a normal force here, and then we can analyze this problem. So the free body diagram of this one is going to the left. Now we need to find out this problem, how we solve the friction, and we look at the unknown. We have P, W, and N, and also the F. So we have 4 unknown. How many equations can we have? For this 2 dimension, we only have 3 equations. So we need another equation in order to solve this problem, and that 4th equation is actually the friction equation. So if we think about the situation might happen in that case, it could happen in 2 different ways. The first way is that let's assume there is a slipping. So the slipping meaning this one actually moved to the right hand side and the whole thing is moving. That is what the slipping means. And we know the maximum friction force is going to be equal to this. If a slipping happen, then your force actually is going to higher than this force at here. That friction will be what we call the kinetic friction, and that will be equal to mu k times the m. But we solve this one just before the slip. If you solve this one just before it starts to slip, and then you can use this force as the maximum friction force, and you have X, you have P, you have M, and you solve that. Can we solve it? Sure, because you have the force equation right here. You have summation F of X, summation F of Y, and you have a summation moment. You pick a point. Normally it will be this point or in the middle point, it doesn't really matter, and then you can solve the problem. However, if you think about another situation is that you push this one and it doesn't move, but it starts to tilt, and that is what we call the tipping. If it is tipping, and where is the point it is going to rotate about? It's going to rotate about at the corner right here. So this will become the rotation point. And And you can find out the distance of this one directly if you know the dimension of the closet. So this one is given. And then you can still solve the problem, and the problem will still depends on the equilibrium equation, and you can use this information to solve the problem. Okay, let's actually look at the real situation here. Let's just say the weight of this box is 250 pounds. The static friction coefficient is 0.4. Again, you can do it experimentally by sliding this box and increase the angle. We can find out tangent theta is going to be the coefficient of the static. We want to find the maximum force they can apply without causing the movement of the crate. So this is the situation of the first situation in our previous slide. We want to find, before it starts to slip, what is the maximum force that will make that situation. So we can draw the free body diagram and simply just four forces, right? There's a weight going down, and there's a normal force going up, and there's going to be a friction. The friction should go to the opposite direction, so this will be the friction force. So that's the free body diagram. And then we apply the equilibrium equation to solve this problem. Let's look at some detail how we do it. So again, based on the dimension, based on the forces that we identify, this is the free body diagram of this problem. The weight, we're going to assume the weight is going to be just right at the center of this object, and which is this one here. It's not going to be just in the middle. You are given with this point. The reason it's not right in the middle is probably you have something more weight, more heavier at the bottom and something more lighter on the top. So the weight is going to be distributed a little bit different. And we're going to assume the crate slips, which is just right before it slips, your maximum friction force is going to be equal to this. So this is the maximum friction force that is equal to mu s times n. You can keep the n over there because we don't know how much n that is. However, if you go to the next equation, you will find out, well, by the summation f of y, the normal force is equal to its weight, and that's the only two forces in that direction. So once you find out n is equal to 250, you can put the 250 into the other equation, that is the P, the pushing force, minus the 0.4 times the n. This is the maximum friction force, and that will be equal to 0. That is the highest friction force that box is not moving, right? After that, it will start to slip. And then you can find out what is P equal to. So we solve these two, we find out the P is 100 pounds. Then if you want to find what is the position of the normal force, and you can use the summation moment. So we, by assuming, well, the normal force is going to be in between this point, which is right below the center of the weight, and between this corner and here. Let's make this position to be x. And we're going to do a summation moment. Now you can do a summation moment at this point, you can do a summation point at this point, and we choose this point, which is the point just right below the weight. The weight has to go through this point, therefore the weight is not going to create any of the moment. The only thing will make a moment is going to be this one here, not this one here, because this one will go through this point at here, and this one here. So you have both the P and N will cause the moment. How much moment caused by the P? Well, it's going to be 100 pounds, and it's going to be turned clockwise, and clockwise will make negative. And the lever on is going to be 4.5, and that's 4.5 multiplied here. For n, we solve the n is 250, so 250 is our n, and we don't know the x, we try to find out x, so here is the x. So once you solve this one, and then you will get the x, and the x is going to be equal to 1.8. So that is the highest, like the maximum length if you put an n over there. If you don't, and then it will probably start to tilt. Let's look at the second one here. Let's think about if this one will tip. What happened if the tip? So this will be the situation that will tip, and when you tip, this is going to be the rotation point at here. We again doing the summation f, summation of y. Summation f of y give me n is 250. Summation of f of x is going to give me p minus f equal to 0, and that will be making the p equal to f. Now, we don't know if this one tip, how much friction that is, so we are going to not use the mu s times n, and just keep the f over there. Now we do a summation moment. Again, you can take summation moment here, but this probably will not help me. And the reason is, if you take summation moment at here, and you have this one, and this one will cause the moment. The way is going to cause the moment go this way. The push force is going to make the moment go to the other way. Then, well, you probably can use this one, huh? Yeah, okay. So if we do that, if I use this point here as the summation moment, I have P times 4.5. That's going to be clockwise, so be negative, plus the way is 250 times the lever arm, which is 1.5, and now be equal to 0. So I can find out the P, which will be simply equal to, let me just cancel one, this one. This will be 3, and this will be 1. So that will be equal to 250 divided by 3. And that is your push force. If this one tip, in the slide it used the O, but I think it's probably is the best to use this corner. I think it's using a corner. Yeah, it's exactly the same equation. So it's actually not this point right here. And you can find out the pushing force. If this is a push force, then your friction will be equal to this, and your friction force is going to be less than the maximum. So this one is the maximum, and because the maximum is 100 pounds. All right, so I just wanted to summarize the situation of the friction at here using this very simple problem here. You have a box on a flat horizontal support, and you have push force going downwards, weight going down, and the normal force going up. Are you going to have any of the friction? No, there's no friction because you don't have any of the component horizontally, so everything just pushed downwards, so there's no friction at all. If you tell your force with an angle, then you will start to have a friction force, and by assuming this one is not moving, your push force in the x direction, the px, is going to be less than the maximum of the friction force. This Fn over here represents the maximum friction force. You continue to increase the angle, so then at a certain point, this push force in the x direction will be equal to the maximum friction force, static friction force, and it will start to move. Once it starts to move, then the friction force will become an F of K, which is a kinetic friction force. Over here, we don't deal with the kinetic friction force case, but you learn it in the physics. If that one starts to move, then you are going to have the acceleration of the box will move to the right. And that is for the first episode. We will look at more complicated situation, which is the wedge situation, in the next one.